Hi everyone, it's Sal coming at you again with another organic chemistry video, and today I wanted to go over something that's a little bit tricky, but I think it will be helpful. It's anti-periplanar elimination, and I have for you this great example of anti-periplanar elimination. You're given two molecules, molecule 1 and molecule 2. They look very similar, the only difference being that in molecule 1 the bromine is on a wedge, while in molecule 2 the bromine is on a dash. Now you're given the following reaction. This molecule is going to be reacting with sodium ethoxide over ethanol, both of them actually. And the question is asking for two different things. Part 1 is asking to provide the product of the following reactions, and part 2 is asking to use a mechanism and explain which stereoisomer will undergo elimination at a faster rate. And part 2 is really the part that I think is a little bit more important here, but let's go over part 1 first, as we need to do that obviously to continue on to part 2. So this is your typical elimination reaction. We can start by looking at the reagent that we're given, and it's sodium ethoxide. Now sodium, we know, is a metal, so the sodium, whenever you see a metal compound like this, you should consider that the sodium has with it a plus charge and the ethoxide group has with it a minus charge, which is going to make this a strong base, and the base will allow it to abstract a hydrogen from, I'm going to number this molecule here 1, 2, 3, 4, 5, and 6, and on the second carbon there are 2 hydrogens present, and this ethoxide nucleophile slash base is going to come abstract a hydrogen here, and this hydrogen will fold down over here, forming an alkene. If we look, and of course this bromine is going to be leaving as well as a leaving group. If we look at the second molecule, the very same thing can actually happen theoretically. We have the hydrogens here on carbon 2, the ethoxide comes in, abstracts this hydrogen, it folds down, and the bromine leaves. So since theoretically we can have the same hydrogen abstraction from this molecule, we should be able to form the same resulting product. So I'm going to go ahead and draw the cyclohexane first. So here's our cyclohexane ring. We know that the bromine left from carbon 1. We know that carbon 2 was where the hydrogen was abstracted, so I'm going to just number the remaining part of this molecule. Of course the methanes were not touched, the methyl groups, so I'm going to just draw them as they were. I'm doing the second molecule, but obviously the first molecule is the same in terms of the methyl groups. And we know that the bromine left, so an alkene formed like this, a cycloalkene. So this is going to be the resulting product of this reaction. Now the question is, the more important question is, which one will undergo elimination at a faster rate? And this is really what I wanted to get into today, is the anti-periplanar elimination. Alright, so let's get right into it. So I moved the question up to the top, and so I'm going to redraw the first molecule here. So we had the cyclohexane and the bromine was on a wedge, like so. We had the CH3 groups. Okay, and the second molecule looks something like this, with the bromine being on a dash. CH3 groups are also on dashes. Okay, so let's approach the solution for this question. We have to use a mechanism to explain which stereoisomer will undergo elimination at a faster rate. Well, we know that hydrogen abstraction needs to take place in order to form an alkene, and the hydrogen can really be extracted only from this carbon or from this carbon in order to kick off this bromine here. The same with this molecule, the hydrogen needs to be abstracted from these 2 carbons in order to kick off the bromine. So what we need to do is figure out the actual conformation of this molecule and see if it's ideal for that hydrogen abstraction to take place. So in order to do that, we're going to have to draw the chair conformation. So I'm just going to simply go ahead and start drawing a chair conformation of a cyclohexane. Okay, and I'm going to number this with this being carbon 1, 2, 3, 4, 5, and 6. And I'll go ahead and correspond this with this molecule up here, with this being the 1, 2, 3, 4, 5, and 6. Okay, so the important thing you need to do here is you need to retain the stereochemistry. And what I mean by that is if the bromine is on a wedge, you have to assign it either an up or a down position, and you have to stay consistent for both molecules. I like to keep wedges on ups and dashes on downs. So I'm going to draw that for you just so you have an understanding of what I mean. The bromine over here is on a wedge, so it would be considered up in my definition. In fact, let me just draw a quick legend for you here. So wedges are going to be equal up and dashes will be equal down for my little chair conformation over here. And since the bromine is on a wedge, I'm going to put it on an up position. And up position is axial on carbon 1. You should know this from your chair conformation. If you're not comfortable with chair conformations, then I'll make a video for that shortly. But for now, we know that the cyclohexane chair has bromine on an up position, at least in the depiction that I've drawn. So let's move to carbon 2. Carbon 2 has nothing on it but hydrogen, so we don't really need to worry about that. Moving on to carbon 3, we know that the methyl is on a dash. Since the methyl group on carbon 3 is on a dash, it should be down according to my legend over here. So going through the chair conformation, we know that the carbon 1 had an up, so carbon 2 must be down for the axial position, so I'm just going to draw that here. If there were a CH3, there is not a CH3, so I'll just draw a hydrogen over here to avoid confusion. Carbon 3 would be up, carbon 4 would be down, carbon 5 would be up, and carbon 6 would be down. These are just the normal positions that would exist on the chair conformation. But I'm going to erase these for just to avoid confusion. So on the third carbon we have a methyl group and it's pointing down. And we know that down on this position would be on the equatorial plane. So I'm going to draw the methyl group on an equatorial plane like this and put CH3. Great. Moving on to carbon 4, there's nothing but hydrogen, so I won't worry about that. Carbon 5 is on a down position because it's a dash, and the down position we know has to be equatorial. So I'm going to draw that over here. It cannot be axial because axial is up, as we've defined based off of our first carbon. So now that we have this molecule, we can move on and look at the very next molecule and see how that would look on a chair conformation. Okay, so moving on to molecule 2, we have here the bromine on a dash. So I'm going to go ahead and again draw a chair conformation. And I'll number the chair the same as the first chair. Okay, so this bromine again is on number 1, this methyl group is on number 3, and another methyl group is on number 5. And so if we look at our legend and refer to it, we know that dashes are on a down position. Since the first carbon had an axial position going up, we know that the down position has to be equatorial. So this bromine will be in the equatorial position in this cyclohexane chair conformation. And that makes sense because if we look at the opposite of the wedge, it's going to be the dash, and the dash is down according to my legend over here. Okay, so let's go to carbon 2. There's nothing but hydrogens on it. Fine. So let's move on to carbon 3. Carbon 3 is in a down position, and if we consider the up and down alternating movements of the chair conformation, up on axial would be like this on carbon 1, 2 would be down, 3 would be up, 4 would be down, 5 would be up, and 6 would be down. Since that's the case, number 3 has up on the axial, so therefore down has to be on the equatorial plane over here. So I'm just going to get rid of these red marks and I'll draw that. Great, let's move on to carbon 5. So carbon 5 also has the CH3 on a down position, and as I've shown earlier, the down position is going to be equatorial on carbon number 5. So we would have it like this. So now that we have the chair conformations of both molecules, we can see some similarities and differences between them. The similarities first are that the methyl groups are in the equatorial position for both of these molecules. The bromine, however, is an axial position for the first molecule, and it's an equatorial position for the second molecule. What does this tell us, and how do we need to use this information to figure out which stereoisomer will undergo elimination at a faster rate? Well, as I mentioned, the first part of the question showed us that carbon 2, right over here, or carbon 6, needs to be the carbons that have the hydrogen taken out from it or abstracted in order to form an alkene like this, so that the bromine can leave. That's the mechanism that's going to take place. Now, I'm going to start with carbon 2 because it's a little bit simpler and it's chronological in sequence. So carbon 2 on this compound, we have two hydrogens coming out of it. One is an axial and the other is an equatorial. So when hydrogen abstraction takes place, and we had sodium ethoxide, this ethoxide would come and attack a hydrogen, either this one or this hydrogen. Question is, which one would it prefer? Well, let's think about this. This hydrogen is an equatorial position. However, it's pointed up if you take a look at it, because the bromine was in up position, therefore axial has to be down in the second carbon, since it's alternating in a chair conformation. Now on the second carbon, since the hydrogen is down, therefore this hydrogen that's in equatorial plane must be up. So when you think about it, I'm going to draw this out for you. The bromine and the hydrogen are actually both kind of like on wedges. Now, if this doesn't make sense to you visually, it will make sense if you draw out the actual cyclohexane. This bromine is like this. On carbon 2, there's two hydrogens, right, as I've drawn. However, if we were to draw the stereochemistry for those two hydrogens, it would look something like this, with the bromine over here. Now, since that's the case, we have to consider steric hindrance, or some sort of a electronic repulsion effect that's going to take place between the ethoxide as it approaches this hydrogen, because this hydrogen is on a wedge and so is the bromine. If I were to visually represent this, it would look something like this. Now consider the fact that the bromine and hydrogen are on the same plane. They're on wedges. At least the hydrogen that I'm given the example for. The other hydrogen is on a dash, as we've described. Now, what does that mean for the ethoxide as it approaches this hydrogen? Let me try to visually represent it here. Here we have the bromine, and here we have the hydrogen. The bromine is the larger atom. So what happens is that this ethoxide group, when it comes to attack this hydrogen, it's going to have a repulsion effect, an electronic repulsion effect between the electrons on this bromine. So what will happen is it will come near this bromine and then get pushed off, and it won't be able to abstract this hydrogen. That's actually what's happening over here between these two wedges, and that's the important concept that needs to be understood about anti-periplanar elimination. Now let's go over what would happen with the other hydrogen that's on a dash. Now for the other hydrogen that's on a dash, we would have bromine, the big molecule, up here. However, the hydrogen is going to be all the way down here, and there's this large distance between them. And this distance is there because this hydrogen is on a dash and this bromine is on a wedge. So what happens is that when this ethoxide wants to attack, it has easy access to the hydrogen and doesn't have that previous electronic effect of hitting the bromine and then getting repulsed by it. In fact, it could easily come through and just access this hydrogen. So keep this in mind when I go over the mechanism. Okay, so we've looked at the first molecule, and we've looked at both hydrogens, both this hydrogen and this hydrogen. And we saw that there is a repulsion effect when the ethoxide attempts to attack this hydrogen here, which I'll just label as hydrogen B. and this is hydrogen A. So when the ethoxide comes to attack hydrogen B, what happens is that since it's on the same plane as the bromine, which is up, there's an electronic repulsion effect between the bromine and the ethoxide, so the ethoxide has trouble accessing this hydrogen. However, if we look at hydrogen A, it's anti to the bromine, and therefore it's easier for the ethoxide to go and attack this hydrogen and therefore abstract it, creating the alkene. So we notice that there is some ease in one of the hydrogens on carbon 2 for the ethoxide to abstract. Now let's consider compound B. In compound B, we also have two hydrogens, one on the axial and one on the equatorial. Fine. So the ethoxide has a choice between both hydrogens, and I'll label them again as A and B just for clarity. Okay, so let's draw out and think about this. Hydrogen A is on a down position. The bromine is also on a down position. That means they are on the same plane. And as I explained earlier, if they're on the same plane, then this ethoxide is going to have a repulsion effect with the bromine. Now, let's look at hydrogen B. Hydrogen B is on an up position, and the bromine is on a down position. However, even though the bromine is on a down position, this is not ideal to eliminate all of the electronic repulsion effect, and we can see this if we do a Newman projection. Here's the Newman projection for a view looking from carbon 2 to carbon 1. Imagine your eye over here, and you're looking from carbon 2 to carbon 1. This would be the Newman projection. And if you look at the Newman projection, it's a little bit apparent that there's still some steric effect going on here. This is hydrogen A, and this is hydrogen B. If the ethoxide were to come and attack either hydrogen, there's still a bromine over here that's going to be conflicting, and you know that the bromine is a bigger molecule than the hydrogens. So if you draw it like this, it's a little bit apparent that there's going to be a repulsion effect between the ethoxide and the bromine. You see here, this ethoxide would have difficulty accessing these hydrogens. So this is something to keep in mind when comparing both molecules. So now I'm actually going to draw the Newman projections for both of these chair conformations, so it's a little bit easier to see which chair conformation would allow for easier hydrogen abstraction. Okay, I've drawn both chair conformations, and I've also drawn both Newman projections. If we look at the Newman projection for A, we can see that the bromine and the hydrogen are anti to each other. If we look at molecule B, we can see that the bromine is not anti to a hydrogen, but in fact it's anti to a methyl group attached to a carbon. Due to this anti-placement of the bromine and the hydrogen, we can say that A would be preferred for hydrogen abstraction, simply because the hydrogen is completely anti to the bromine, which allows the ethoxide to come and abstract the hydrogen more easily than it would if the hydrogen were over here or over here. As you can see, the bromine is a large molecule and it takes up this space, so the ethoxide would have difficulty accessing this hydrogen and this hydrogen. Whereas over here, this hydrogen is only surrounded by this CH2 and this H, so there's not that much steric hindrance going on here, and this hydrogen can be abstracted, it'll fold in, and the bromine will leave, forming the alkene. So to answer the question, compound A would actually result in a faster elimination simply because of the anti-periplanar, and I'll write this out, the anti-periplanar elimination of the hydrogen on carbon 2. And if you look at compound B, it is also possible for the bromine to leave if either of these hydrogens are abstracted, but due to the steric effect of this large bromine, the rate will be significantly less than compound A. In fact, the rate difference is more than 10 times faster in compound A than in compound B. I hope this video was helpful for you. If you have any questions, please leave them in the comments section, and as always, like, comment, and subscribe. Thank you for watching.